Welcome back to elementary statistics. This video is on probability distributions, which you'll sometimes also hear referred to as theoretical distributions. A probability distribution is the bridge between the probability theory we've talked about in the last few lessons and the ideas of statistics we were talking about earlier in the course. We can use the ideas of probability to get theoretical exactness of the population of certain distributions, certain kinds of variables that are going to involve the kinds of toy experiments we were talking about in our lessons on probability. Rolling one or several dice, flipping some coins, drawing a number out of a pot, those sorts of things. Let me get my head out of the way and let's start off here with the idea of a random variable. A random variable is about the worst named thing in all of mathematics. A random variable is not random. A random variable is also not a variable. If that makes no sense to you, join anyone else who has ever studied probability theory. A random variable is a rule which assigns a value to each outcome of an experiment. If you've studied in algebra and you're comfortable with the idea of functions, a random variable is a function whose domain is the sample space of the experiment. Again, if you've not studied a lot of algebra and that isn't very comfortable for you, that's okay. Technically speaking, studying functions to that level is not a prerequisite for this course, but I know that a lot of students who take probability and statistics have done work with functions in the past, and if you're one of them, that might be an interesting tie-in. And the idea of a random variable is actually something we have dealt with in the past. Consider the example of rolling two six-sided dice and adding together the value that appears on each die. We can list out the many outcomes. I could get a 1 on the first die and on the second die. And when I add those together, I get 2. I could have gotten a 1 on the first die and a 2 on the second die, or I could have gotten a 2 on the first die and a 1 on the second die. Those two outcomes both give me a value of 3. The outcomes of 1, 3, 2, 2, and 3, 1 all have a value of 4. You add 1 plus 3, you get 4. 2 plus 2 is 4. 3 plus 1 is 4. I'm going to do one more. 1, 4, 2, 3, 3, 2, and 4, 1. I'll give a value of 5, and we could keep going and write out all of the possible results of the two six-sided dice and add them together and get the value. And I've grouped these together in a convenient way so that all of the outcomes that have the same value when we add them together are all on the same row. This gives me a couple of interesting advantages. First of all, it is a nice, sorry about that. First of all, this is a nice visual representation of the relative probabilities. Out of all of the outcomes, there's only one that gives me a value of 2, while there are 6 of them that give me a value of 7. So 7 is far more likely of a result than 2 is. It also gives me a nice way of thinking about these things grouped together. If I take all of the outcomes that give a particular value and I group them together as events, I form what's called a partition on the sample space, right? Each of these values can call from exactly one outcome, and I said that backwards. Each of these outcomes has exactly one value. We've got a number of outcomes that can give a single value, but each outcome, like the 4, 2 here, only has one value associated with it. And so you'll never have an outcome show up more than once on the list. This list of outcomes, if we take each row as a separate event, is a partition. No outcomes show up in more than one event. Every outcome shows up in at least one event. And that's how I'm going to build from a random variable. Right? A probability distribution is built from a random variable. Our outcomes are grouped into events. And in the example of rolling two six-sided dice and adding the result together, the possible events are we get a total of 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, or 12. And looking at the list we just finished, we can count up that there are 36 different outcomes. So the probabilities here are 1 out of 36, 2 out of 36, 3, 4, 5, 6 out of 36 for the outcome of 7, and then it starts going back downward. 5 out of 36, 4, 3, 2, and 1. And of course, most of those fractions we can reduce. 2 out of 36 is 1 out of 18. 3 out of 36 is 1 out of 12. 4 out of 36 is 1 out of 9. And 6 out of 36 is 1 out of 6. What I want you to notice here about this probability distribution, and it will be true of every probability distribution, It looks a lot like a frequency distribution, except instead of having a count here, we have a fraction. So the probability is standing in for the frequency. The event is standing in for the result. But it's still the same basic idea. Although using the tools we've talked about with probability, we can put a couple of restrictions on this. We know that for each event in the distribution, the probability of that event has to be somewhere between 0 and 1. That's just the nature of probability. The probability of anything occurring is a number between 0 and 1, which we often write as a fraction or as a percent. The other thing we can take into account is the idea that these events partition the sample space. Every event is represented exactly once. And we know that in total, something has to happen. If I add together the probability of every event that is possible in a probability distribution, I need to get 1. There is a 100% chance that something happens when you perform an experiment. And a probability distribution is always set up so that things are mutually exclusive. We have that partition. Right? One of the takeaways for that, you cannot have a probability distribution where you have unrelated kinds of events. Right? In the experiment of drawing a card from a standard deck of cards, you might set up a probability distribution about drawing a heart, a diamond, a spade, or a club. You might set up a probability distribution about drawing an ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, or king, but you could not have the event of drawing a jack and the event of drawing a heart in the same probability distribution because the jack of hearts exists and would fall into both cases. All right, so our events have to be mutually exclusive and they have to be exhaustive. Everything that can happen has to be represented in our probability distribution. Otherwise, what we have is not actually a probability distribution. It seems fairly straightforward, I hope. Helps if the button to make me go away actually makes me go away. All right, as another example, I might be interested in the experiment of flipping a fair coin 4 times and counting the number of heads. If you are not quite familiar with this experiment, we can list out all of the possible outcomes. It turns out that there's not that many. Right? The first coin could be heads, the second coin could be heads, the third coin could be heads, the fourth coin could be heads. Or maybe the fourth coin came out tails. Or maybe the third coin came out tails, in which case the fourth coin could have come out heads or tails. Or maybe the second coin came out tails, in which case the third coin could come out heads and the fourth coin heads or tails. The third coin could have come out tails and the fourth coin either heads or tails. Or possibly the first coin came out tails. All right, so there are all 16 possible outcomes for flipping a fair coin 4 times. If I count the number of heads, I get that there could be 0, 1, 2, 3, or 4 heads. 0 heads occurs 1 time. 1 heads occurs 1, 2, 3, 4 times. 2 heads occurs 1, 2, 3, 4, 5, 6 times. 3 heads occurs 1, 2, 3, 4 times. And 4 heads occurs 1 time. So we can take this experiment, we can list out all the possibilities, and we can use that to write a frequency table, which we turn into a probability table by taking each of those frequencies and dividing by the total number of possible outcomes and reducing the fraction if possible. Right, so 1/16, 1/4, 3/8, 1/4, and 1/16. We can also take a probability distribution and we can sketch a graph much in the same way we sketch the graph of a frequency distribution using something like a histogram. All right. So that's the basic idea of a probability distribution or a theoretical distribution. Uh, Problems for right now are just going to be constructing a probability distribution given the ideas of finding the number of possibilities, thinking about all the rules we've been talking about recently on how to count things, right? How do you know that you have every possibility here when you flip 4 coins? Well, each coin has 2 possible outcomes, and you do it 4 times, so 2 times 2 times 2 times 2 is 16. I know there should be 16 things. I list them all out. I get 16 things. I must have gotten everything. All right. With that, I'm going to wrap this one up. And I'll see you next time when we're going to go on and dig into some properties that we can build off of for probability distributions.